Good morning, ma'am. I'm screen recording my mom's computer so that you can see more of what or more of the stuff at once because my laptop's a bit small. So I'm just quickly catching you up on what I've done so far and just the results and things that I need to get a bit of input on from you. So on the right here is the paper that the Roy Billington test system was built off of. So it's feeder 4 and feeder 2 were added. And then I made my own sort of sketches of them and updated them so I could see all the components more accurately. And then those systems were then recaptured in Excel using sort of a connection array, if you might, where every component is given a repair or switch designation or a 0 if it's not connected at all. So that each load point, so let's say load point 1, that if component 1 was to fail, it would be a switching time. If it's 0, 0, obviously it's not connected at all. And then their repair times and failure rates were captured here in this table, and all of that gets exported with my code into the Python little file that runs the Monte Carlo simulation. So this is system 4, which means it's feeder 4. I also have the screenshot over here. So it's the system here, just flipped so you can see it more clearly. I simulate the whole system at once, and it does it in about 4 minutes. For about 10,000, no, it's for about 1 million years in total, just to get the accuracy more accurate. And all of this gets sort of sucked into a Python file, which is on my other laptop. For now, I would show it here. It's just there's a lot of stuff on the screen already, and then it runs through the simulation, and then it outputs it into this Excel sheet here, which is just the results spreadsheet. So it takes the FEMA results and it takes the simulation results and puts them next to each other and then adds an error, or it checks the error for me. The red are just where I've put in anything above, I think it was 0.75%. So the error bar here is just a percentage of what it is. These values here, the FEMA ones, come from my original system data where I did the whole system FEMA here. It's in the same way, I hope you can see them here. And then it gets scrolled down. It's quite a large thing, but this is because there's, in this system here, 196 components. So it does all of that in one go here, and then generates the FEMA table for me here, and then obviously does the SAFE, SADI, and all that down here. And that, coupled with this, using the Monte Carlo simulation, is exported to this file here. So you can see for load, so this shows feeder 1, it's quite a large feeder, it's got 7 components, it's this feeder just here, so it's got just the 7 load points on it, and then the transformers plus the 12 lines. And if I remember, yeah, so it's the double-sided one, the double-sided isolator switches here. In any case, all of that gets printed next to each other so I can see the performance of the sort of FEMA versus the simulation. So you can see, for instance, the FEMA has the unavailability for component 4 for load point 1 at 0.49, and then the simulation found it there. And this is the percentage error for the two, is 1%. I believe this one is a little bit inaccurate just because I think I only ran it for 100 simulations of, I think, 1,000 years, so it's not as accurate. And then all of this, so that every feeder here gets, so this is feeder 2, that bit there, and then it continues, you can keep scrolling to the right, and then it gets to feeder 3, which is this component here, and then obviously feeder 4, feeder 5, feeder 6, and feeder 7 is here. But just to scroll back to feeder 1, just to show you how it works. Then it outputs just the indice tables for me, so it does the FEMA version of it, which it takes the data from the FEMA table and then generates the SAFE value here, and then the simulation, and then does the error again. It does it for SAFE, SADI, KD, AU, I'm not sure how to pronounce it, SI, the energy not served, and then the average energy not served, and then the cost, and that I'll get to in a second. I just want to show you that these values are accurate in terms of what Roy Billington said. So these are the indices for this particular, so this is just the base case. I can easily, with the benefit of this table here, alter the case type that it is. So it's disconnects, fuses, and alternate supply. You can change that quite easily to another type of connection with this. Back to the results. So for instance, load point 1, these are in feeders, so this only takes these feeder totals here at the bottom. So for instance, feeder 1 is the safest 0.302. Oh wait, this is system 5, sorry, gotta go back to 1. So here is the safety. So safety is 3.2, 3.2. It's off by 0.1. So there's that. And then the SAIDI is 3.47, 3.468, and then 3.47. His values up here are from the Monte Carlo simulation as well. So they're not from FEMA values. That's why there'll be a slight discrepancy between the two. And then the SAIDI 11.5, and this is off by a little bit because of the simulation error that would have occurred between our two simulations. And then the ASUI, again, this is a very small value, 0.0396, and it needs to agree with a very small error. The ASI 099604, and then these agree because of how large this data value becomes. It's quite easy to get it quite accurate. And then the energy not served is 12,192, and it's 12,196 in his case. And then the average energy not supplied is 11.09, and in my case it's 11.08, with an error of less than 0.16%. So that's my update for the reliability indices stuff. And then to get to the cost stuff here, I started working using his second paper that would introduce the system reliability worth indices to the same table. So we can see here, let me just scroll a bit down. This is supposed to be, I think it's bus 2, because it's only got the 4 feeders, so it is this bus here, and that's the system here, by the way. So it's also got its exact same results as the other one because it was also captured in here. So system 5 is my bus 2 here for that system, and then all of its data is captured in here. So that is all captured like that, and he introduces these 3 indices here, so that's what I was putting over here to be filled. And how I did the previous ones was I used small increments, so I used the smaller system, so let's say just this feeder here. And I realized when I was reading through some of the older papers that one of the papers that we were interested in for furthering on, because Prof. Gaun's one paper used the beta distribution to mimic different distributions. So I decided I'd use his paper as the testing ground, but the problem was that I started finding a few, I didn't understand some of the terminology he used and methods that he used. So this is just the power system network for bus 2 feeder 3, so it's this is bus 2 the whole system, and then feeder 3 is this feeder here, and that's been accurately recreated without the alternative supply over here, and with the little blue, I don't know if you can see it very accurately, the blue indicates isolation switches on that side. And so he created, this is actually from his master's thesis here. Let me go to this paper. Actually, well, I can show it to you a bit more accurately here. So this was a case study that he did using the reliability data he used in his surveys above. So his master's thesis was a dual paper with cost analysis sort of surveys done above to create the table over here. So this is the mean, the duration, and the mean cost, and then the beta parameters. And he used this MATLAB code to get that. Let me just get back to these so we don't have to get too much change. So this was his, so this case study that he did here used that data above in that paper to create this. And so these were values that he himself sort of theoretically created, just to give this a bit of a case study, some substance. And these are obviously just parameters you'll use to create this sort of setup where you create the reliability component indices. And then this all makes sense for me in terms of what was even said in the this work. It all matches the algorithms, the component layout, and all of that makes sense to me. What I'm struggling with firstly was this small deviation from what normally happens, where he's got a load point with 2 separate types of customer types on it. So I'm not too sure how to account for that in terms of, I think you have to use something similar to what he uses, that Roy Willington suggests here. Or was it in the second paper? Oh yes, it's over here and this one. So he suggests making a load point customer damage function, where you simply sum up the individual customer damage function. So if you have 2 customers, you obviously have individual for 2 of them, and then the percentage that they're getting off by, and that creates a localized one for the load point. But I'm not too sure how to incorporate probability distributions within that, because this here is taking into account that it's a sort of a linear extrapolation. So you can just add the two together and then divide that by 2 to create an average. But with probability density functions, I'm not too sure how to collect the two in the same way that this would work. But that's a smaller problem that I can figure out in a bit. Oh yes, so back to this paper here. So he uses this cost A C FHD FM CAD, which is obviously, this is just the weighting factor for the hour of day and the day of the week. The FM is just the month of the year, and then this is your average. CAD is your average cost, worst case cost. It's up here. There's a better word. Reference cost, sorry. And he takes it from his worst case power interruption cost, and then he takes that from these particular days, and these weighting factors all make sense to me. And I've been able to export this system into a cleaner function with the same load point connections, component failure rates, repair times, switching times. So I can change any of this with the distributions as well. And then this is just feed information for my own purposes. When I generate outputs, they need to be in a certain format so that you can read it more easily. All of that comes to this point here, where in the original way of working out your E-cost is made up of your scaling factor, so your time of day, time of month, and so on, your cost, so your damage cost, times your load profile. In Oliver's paper, he uses the load profile, as, let's go a little bit further down, as the average electricity bill here. I will talk about this in more detail in a moment. I just also, with regards to his MATLAB code, because this didn't make sense to me. But I understand if we use this as his load profile, that's perfectly fine. So that gives us our L. So if we go here, that gives us our L version of our cost. The problem is that he doesn't explicitly say, either in this smaller conference paper, also, I think this is actually I think it's actually from a journal, but in any case, it doesn't say where he gets it. He just says up top here that he gets it from his surveys at 4, but this 4 doesn't link up to his references down below, because 4 here is supposed to reference his thesis, but it's actually this value here, so it's actually supposed to be 5, but in any case, actually no, I think it's supposed to be this one here. This is his master's, it's supposed to be 6. So in his master's paper, if we scroll back up, this is where he gets his values from, his hour distributions. And to explain how he gets his cost damage function, we have to look at his MATLAB code. So this here is his E-cost value, if that makes any sense. Maybe this paper will explain it a bit better. So his cost value here equals previous cost plus, so that the previous cost is C1, and take it for granted that this is looking at just one particular load point. So he did load point by load point for each one, and we should probably scroll down because there's 3 different cases that he uses. Oops, sorry. In his approach, he looks at, because in this paper he's simply trying to explain the E-cost, the differences in E-cost from approach 1, where they don't include any time variation, with approach 2 and 3, where they include time variations. And then in the third approach, he includes a beta distribution to scale it even further. So in this case, he's got his load and his cost. The problem with his cost function is that and it gets that cost CI value over here, is that this is the previous cost, so this is a simulation that accumulates over time. And in this case here, he's just simulating, let's go to his thesis. So that 1.72 comes from this table here. It's a summary of all of his data from the 4-hour value, and then he scales that up and down. So this is base 2, this is where there's no beta distributions included. So now if we scroll a bit further down, this is the second case. This is now where they include time variation, and he includes all of that with these weighting functions here. And so here, if we go back to the cost function, so here L3 is regarded as his month of the year, and then L4 is regarded as his hour of day and day of the week. And again, he takes just the scaling factor here of the duration, minus 4, since it's at the 4-hour mark here, times it by 0.95. I think that's the linear relationship between the two I was under the impression we were supposed to do log-log interpretations between averages like this, but that's something I'll have to ask him to elaborate a bit more on for me. And then he adds that total cost function to create just his C1 value. So this is just his CI value. The problem is that when we go down, so this is just the different components failing and what costs they are attributing to the overall load point. So here he does the sort of condensing of the simulation data. So here he adds all the failure rates, the unavailability. And the problem is that, so here his cost function comes in, but these do not include any load. So it didn't include any load data here at all. As far as I can tell, if we look at just this example here, this is your weighting function for the month of the year. This is your day of the week, as well as the hour of the day. And then this is just your average damage. So I'm not too sure if they've already accounted for the load in this value already or not. Because it comes from this value here, which is the summary of outage costs for different custom segments. I thought you were supposed to take this cost damage function, so that's this bit accounted for here, and then multiply by the load as well. I'm not too sure what happened there. So then your cost then gets added up for all the different components, which is fine if you had added the load, and then it gets instantly added to your e-cost value, which then here gets averaged out for that particular simulation time period. And then at the end of the simulation, it gets added to the total system here, which is, so here's your E again from your E cost. And that just gives you your average of averages. And then it gets outputted here. And that's the end of the, so this is now where they include the beta function. So here they start again, doing the entire process going down. Here, these are supposed to be separate, and I'm fine with them taking just a singular beta parameter. One of the things that I'm a little hesitant to agree with is the fact that he's got a minus beta. Those are supposed to be positive, so I suspect his derivations of those were inaccurate or different, because if we look at, I'll look at his later paper that he wrote, I'm not too sure when, those got fixed. But in any case, so he's using these as his cost function now. And he's doing the same cost sort of algorithm he did before with the month of the year, the day of the week, and the hour of the day. And then this is supposed to be your cost parameter that gets captured by this beta distribution. So it creates a random number that it scales then. The problem is that this doesn't include any scaling or location points, so I'm not too sure how to account for that with these. I'm not too sure if perhaps MATLAB does that for him, and that's why that's in -3 point there. Because from my understanding, these only get shifted if you put in a location and a scaling factor here, but that's another paper's problem, I guess. And then he had the same thing here, and then all of a sudden with these two papers here, he just included a 25 and a 10 up over here. So I'm assuming those are his scaling factors, but I'm not too sure why these are for these particular, these two sections. So these have all just been 1 up, but these two have been 10 and 25. And then he does the same process of collecting the data. I don't see where he's included the load in these at all. I know that they're supposed to be normalized, but in this paper, he explicitly says his load model comes from this table here. So I don't see where 6, 3, 15, and 20, 2.78 have been included in this cost model. So that's just from his paper's perspective. I'm going to probably take a step back from this paper and just start working originally with these again, and then using his cost data to get these load points instead of what he was doing, so I can show that it works with this particular bus. And then what I suggest as my final bit of work is looking at both Matembula's and Hierzo and Onumusa's papers. They both looked at 2 real-world systems, both C-Point and at Filippi. I can take these same papers, these same networks, because they only did reliability indices with these, and apply the e-cost same analysis to these, and look at the outputs from them, just to show real-world applications. So in Oliver's paper, he has real, Should not have moved that down. Leave that there. Move that back. So these have got particular loads on them. So for instance, these should be your residential papers. I don't know why you put it upside down, but it is upside down in this paper. So these all have loads connected to them, and I can take what he's placed in this paper in terms of, all just in his thesis, these average distributions, because these are for particular types of business, and apply those same factors here, to these papers. Or I can also take, in this paper, they've also presented other cost functions, and these include residential costs as well, and I can apply these to these real-world systems and see what the outputs from those would be. And then lastly, there was another paper here that he wrote. This was the one that he wrote, I think, a bit later, in terms of when he presented his original master's and that paper versus what this paper was for. I haven't found exactly where it came from, but he uses that same cost data. So these values here now have been used and properly scaled, so I assume he's upgraded the ways that he's connected the two. But this is now using that same system, feeder 3, over here, and here he's now included beta distributions for the costs in terms of what he should have done over here, but these are now completely different from his original. So in his original paper, let me drag that over here, his beta distribution for a summer weekday. So this is a summer weekday morning outage cost for different segments. So for the retail, for a 1 hour distribution, he's got 0.3, and so I suspect he changed his method of creating alpha and beta values to what they should be, to include location and scaling, which is that 30th there. So this paper is much more accurate. The only reason I didn't start this paper yet was because I wanted to understand what he did in his original one. And so yeah, I might start on this, or I can start finishing up the cost analysis using these algorithms instead. They're one and the same, it's just the data that they input. This versus these inputs. So in this particular paper, they don't use any probability density functions, so I should probably start with this because it's just averages. And then in this paper, they've included distributions, so I think this will be my second paper. That's an update on everything I'm doing at the moment. So yeah, this is just a little showing of the introduction of the weighting factors into the spreadsheets, because they get sucked into the Python file as well for Monte Carlo simulation. So hopefully I can finish that by tomorrow or the day after, so that I can show you the results for the e-cost stuff. I would preferably like to be able to do it for this particular system so that you can see it versus, because I believe he outputs, yes. So here he has all the load points and their e-cost value here. Yeah, and that's everything. I hope this format works. I will link all of these papers if you'd like. I'll definitely send you the system data file and also the spreadsheet here with my particular results so that you can compare them with what they found here if you need more comparisons. And let me know if I have anything else I can get you.